Greetings and welcome to the Chemistry 222 Molar Mass Determination by Freezing Point Depression Lab. Another lab with way too many syllables, probably for its own good. So let's call this the Freezing Point Lab. I think that'll be a little bit better. This lab is pretty cool for chemists. We looked earlier at the way to find the molar mass of a volatile liquid. And if your liquid can easily be turned into a gas, that system works really well. But a lot of compounds, that's just not very reasonable, all right? Either they're too difficult to make them boil, or you'd have to have such extreme temperatures. And sometimes compounds will break down too. So this is another technique that a chemist can use to find the molar mass of a compound. And this one involves the freezing point. And this is a solution property. If you have a solution, the solvent in the solution will freeze at a lower point than the solvent will when it's by itself. And scientists can use that change in the freezing points to actually find molality, then moles, then the molar mass. It's a pretty cool technique. So this is a lot more versatile than the volatile liquid molar mass process. It can be used for a lot of different things. And also there's the boiling point elevation type problems, which are similar to these. This is a pretty cool technique. So anyway, without further ado, let's get into the lab. In this lab, the goal is to find the molar mass of a solute in a solution, all right? So the solution will be like usually the liquid part, and the solute will be like some kind of grams you put in. It's not always that simple, but this one it is. Freezing point lowering, freezing point depression is one of what they call the colligative properties. It's a colligative property of solutions. Solutions behave differently than the pure substances do, and scientists can use these changes, these colligative properties, to find out some pretty interesting kind of stuff. So let's say that normally the solvent froze at like 10 degrees Celsius. When we put our unknown in, the solution might freeze at like 7 degrees Celsius. So it would be 3 degrees lower than the normal freezing point. That's the kind of thing we're looking for here, which is cool. In the freezing point type problems, the equation that's used is delta T equals K times M times I. The K is an FP. We'll talk about that in a little bit. The delta T is literally the change in the temperature between the solvent and the solution. So in the previous example, the solvent, I think I said, froze at 10 degrees Celsius, and the solution was 7 degrees Celsius. So the delta T would be a change of 3 degrees. KFP is what they call the freezing point constant, and it's something that depends on the solvent. There is also a KBP, a boiling point constant, for a lot of these solvents. So I put the KFP on there just to make sure that you use the right freezing point constant. There's different ones. Don't use the boiling points. Now, in all fairness, there's only one solvent in this lab, so it's not going to be difficult to figure out what KFP is. But if this was the real world, make sure you use the freezing point constant for the solvent. Little m is the molality of the solution, and molality equals moles of solute over kilograms of solvent. And molality is kind of the first step in solving a lot of these. And finally, I here is called the Van Hoff factor. Now, Van Hoff factor is really important when you have an ionic compound, like sodium chloride breaks up into sodium ions and chloride ions. So 1 mole of NaCl makes 2 moles of ions. The little I factor is to figure out basically how many ions there are from a given solute. In this lab, though, everything is organic and covalent, so I is just going to equal 1. So really, you can leave I out of everything in this lab, and that's honestly totally fine. Again, molality is moles of solute per kilogram of solvent. Quite different than molarity, which we've been using pretty much up until this point. But anyway, what we'll do first is we'll solve for the molality, and then if we know the kilograms of our solvent, we can then find the moles of solute, and then if we know how many grams of solute we put in, grams divided by moles will lead us to molar mass. So again, this is pretty handy for this kind of procedure. If you wish to find a molar mass, you'll probably have better luck using freezing point or boiling point than you would the volatile liquid. We need to talk a little bit about what is freezing. And that may seem a little silly because you think, oh yeah, I put my liquid water in the freezer and it turns into an ice, duh. Well, it's a little bit more than that because when you freeze something, the liquid doesn't just instantly turn solid. All right, it's a gradual process. And so those graphs right there shows both a solvent and a solution. And initially you have a very steep curving part. So you can see it goes down pretty steep there for a while. But then you get to the point and the cooling becomes less more mellow, more gradual, okay? And the point where those two lines come together, those are really the freezing points. Freezing point means that the conversion of liquid to solid has begun, but it doesn't mean necessarily that all of the liquid has turned into a solid at that point. And that's very, very normal. So what we're going to do to figure out freezing points is we're not just going to look for when the solid appears, we're actually going to graph the data. We're going to have a lot of temperature versus time data, okay? And you're going to actually see these kind of curves like you're seeing in that picture right there. And from the point where the two lines intersect, that's going to be the freezing point. So for example, here it would be right there. And in the pure solvent, it would be right there at that point. You'll notice that there is a little bit of a curve right there in the bottom, and I kind of ignored that. That's what they call the supercooling effect. It's something when sometimes the solution is cooled too quickly. You don't need to worry about that, but if you do see a little bit of supercooling effect, just ignore it for this lab. It's not a big deal. However, we will be making some graphs. They're going to be temperature versus time graphs. You don't need to perform a linear regression in this lab, but you do need to visually figure out where those freezing points are. And again, notice how the solvent freezing point is a higher temperature than the solution point. So this point would be a higher temperature than that point, and that's what should happen. Freezing points of solutions will be lower than the freezing point of the pure solvent. So again, to find that freezing point, it's the midpoint between when the cooling slows and the actual freezing. The slopes of the two lines are different, all right? But again, you don't have to do linear regression. I would just visually look at it, and you want to see again where those 2 points kind of come together. And again, in this graph, notice how the solution has a lower freezing point than the pure solvent. And that's what's supposed to happen. Solutions will have lower freezing points than the solvents they came from. They would also have higher boiling points than the solvents that they came from too, but that's not important here. For us here, we just want to figure out what the freezing points are. And the difference between those 2 points, between the freezing point of the solvent and the freezing point of the solution, that's going to be the delta T. And over here on the left, you can see delta T equals K times M times I. We don't need to worry about I. We're first going to solve for molality, etc., etc. In the actual lab, all right, if you're going to do this actual lab, you'll heat the solvent to the liquid point. So when it turns completely liquid, then you're going to cool it. And you're going to cool it until it goes beyond the freezing point. You're going to monitor the temperature with time. You're going to record the temperature every 30 seconds or so. Once you go through that, then you'll reheat it up. You'll make it all go back to liquid. Only this time you're going to put in a solute. And the solute in the solvent makes the solution, and it looks just like a liquid like before. But again, like before, with the solution, you'll just cool it down every 30 seconds or so, take a temperature, and you'll see that the points kind of mellow out until you get past the freezing point. Once you have all this data, then you need to create a computer-generated graph, and it'll be temperature on the y-axis and time on the x-axis. Now, you will have 2 sets of y-axis data on the same x-axis, and I'm going to show you a little video here in a little bit of how you can do that. It's very easy. I'm going to do it in Excel, but you could also do this in Numbers or Google Sheets or anything like that. That way you can visually see what the freezing point temperatures are and stuff. And then finally, you'll get the delta T from the graph, the differences between the 2 freezing points. KFP will be a number that's given to you. I factor, again, is 1 for this lab. So what you'll do first is solve for molality. That little m is moles per kilogram. So if you multiply by the kilograms of solvent, that's going to get just the moles of solute. And because you knew, hopefully, how many grams of solute you entered in earlier, grams divided by moles will give you molar mass, and you're good to go. Okay, in this video, I'm going to use Microsoft Excel on my Macintosh computer to show you how to graph data where you have 3 separate y-axis data streams. And so you can see in this video on the left-hand side is time. That's going to be our x-axis. And then the second column there is the lauric acid, the solvent. The third column is the first benzoic acid sample, so about 1 gram has been added at that point. And then finally, the fourth column there is the second benzoic acid sample. So you can see they're all temperatures in columns B, C, and D, and we're going to graph that into one place. And it's actually pretty chill. Most of the time on these programs, and you can use Apple Numbers, Google Sheets, or as I'm using Microsoft Excel, what you want to do is select all of your data, okay? And notice how columns B and C, they're missing some pieces at the bottom, but that's okay. Excel and these other programs are smart enough to figure that out. And what we want to do is we want to make an XY scatter graph. So in this version of Excel, and again, yours might be different because I swear every one of these is a little different, I would go insert, and then there's different kinds of charts, and the one that scientists like is usually this one. You want what's called an XY scatter plot, and you don't really necessarily want any points or any lines, excuse me, on it, but you can use this one which has lines too, but we'll see how that's not maybe as helpful. So I'm going to pick this XY scatter graph, and here it is, and that's not bad. Okay, on the y-axis you can see those are temperature values, and on the x-axis here, those are time values. And you're welcome to make it fancier and change things around. However, one thing that you must do is notice how right now the y-axis starts at 0 and goes up to 60. And if you look at all of our temperature data, the lowest temperature value we have there is 36. So we want to change the y-axis so that the graph itself focuses on the data. Like, you have a lot of dead space in this graph, and it's hard to see patterns when you have it listed this way. So what you want to do in Excel is you want to double click on these points, and on the right hand side you see this thing that says axis options. Now right now the y-axis is selected, make sure that that is, but we want to do this a little bit better. Right now it's going from 0 to 60 and there's lots and lots of dead space. So what I'm going to do is I'm going to have the minimum be 35 because that is lower than the lowest temperature we have there in column D. You can see the lowest one is 36. And for a high, it thinks 51 is fine. I'm going to make it more whole numbers of 5. I'm going to make it 55 degrees. And you can see now what happens is it does make the graph really nice. Now, to be honest, I think I like Excel's version of 51 better because now we have a little dead space at the top of that graph. So if I change it to 51, yeah, now everything's really good. And you can see there how the points are converging. This top part here is the lauric acid, so the freezing point would be right about there. The first benzoic acid sample, which is here kind of in orange, would be somewhere in here. And then finally the third set of data, which is the second benzoic acid, would have a freezing point around there. And this is what you want to use in your graph. All right, you want to have a nice expanded graph, and you want to make sure that it's big and stuff so it's easy to see. And then using a pencil or something like that, you can actually then discover what the freezing points are and mark on your graph what the freezing points are. Should be no big deal. Because I am the quote-unquote lazy chemist, which means I don't like to sometimes mess around with a lot of values, I'm going to share with you an equation that I use sometimes on this lab. And it's basically a quick way to find the molar mass of your solute. And the molar mass equals G times K divided by delta T and the kilograms. So MM is molar mass, the grams per mole, that's what you're looking for. Little g is the grams of solute, and that's a measurable amount that you'll add into the solution to see what's going on. KFP is the freezing point constant. It's solvent dependent. Delta T is going to be the difference in freezing points between the solution and the pure solvent. And finally, the kilogram there, that's the kilograms of solvent. You may need to turn grams into kilograms, but that's no problem at all. One more thing too, both molality and molar mass involve mass, grams. And for that point, they must be positive numbers. So if you had a delta T which was negative, it's totally fine, but when you get to this point, or when you get to the point of molality or grams or something like that, make sure you absolute value it. You don't want to have negative mass, negative grams. You don't want to have negative moles or negative molality or negative molar mass. One nice thing about chemistry is that mass is always positive. So if you see any negative masses, just absolute value them and we'll all be good. Just to make sure that we're all on the same page here, I have some sample questions that I think might prove helpful in this lab. So you can see on the left-hand side there's a graph with 6 different points labeled A through F. And the first question is, which letter corresponds to the freezing point of the pure solvent? And if you remember from the ideas of freezing point from this lab, the solvents have a higher freezing point than the solutions. This is the depression of the freezing point depression. It should be lower. So in this problem then, we would expect B to be the freezing point of the pure solvent. It'll be higher than the solution, which is the red set of dots under it, and that'll be important to us here in a little bit. The next question says, which letter corresponds to the freezing point of the solution? And like we just said, the solution is going to be a lower freezing point than the solvent. Now I forgot to mention, but freezing points are always at the conjunction of those two lines. So you can see, like on the pure solvent there before, there's like a straight line. This is like normal cooling of the stuff. And then there's kind of like a steep line. And it's where those points come together. That's where the freezing point is going to be. Now on this, which is basically made up data, it's easy to see. Yours might be a little tougher, but it's the same idea. You want to try and look where there's conjunction of two lines, all right? And where those lines come together, that's going to be the freezing point. So back to the question, the letter that corresponds to the freezing point of the solution would be E, all right? E is lower than B, the freezing point of the pure solvent, and that's the idea here. Solutions have lower freezing points than the pure solvents that they come from. Now finally, if you wanted to know what delta T is for this question, delta T, if you're using a positive K, will be a positive delta T as well. So what you want to do is look at the freezing points of the pure solvent, and if you kind of go over there from where B is, you can see that's right about 53 degrees. That's going to be the freezing point of the solvent. Now the solution, what you would do is go over to right about there. On the graph, it looks like it's between 49 and 51 and about halfway, so it should be about 50 degrees. And delta T is literally the higher one minus the lower one if you want a positive delta T. So in this case, it would be positive 3.0 degrees Celsius. That's the delta T that you want. It's not the freezing point of the solvent or the freezing point of the solution. It would be the change in the freezing point between the two of them. Here's another example that might be kind of helpful. In this problem, we have an unknown compound, 0.4978 grams. It's dissolved in 5.0036 grams of naphthalene, which has a freezing point constant. Now, normally naphthalene freezes at 80.1 Celsius, but in this case, the solution is lowered to 75.0 degrees Celsius, and we want to calculate the molar mass of this unknown compound. And this is kind of like what our lab's going to be in a certain kind of way. So the solution, now of course it's kind of a joke because solution is what we have, but it's the solution to the problem. All right, if you get it, cool. If you don't lose any sleep over it. Anyway, I would use this. The molar mass equals G times K divided by delta T and the kilograms of solvent. Now the grams of the little g right there, that's going to be this 0.4978 number. That's no big deal. KFP is the freezing point constant, and that'll be given to us, which is in this case 6.8. We want to divide by delta T. That'll be the difference between the freezing point of the solvent, 80.1, and the freezing point of the solution, 75.0. So like on the last example, we'd go 80.1 minus 75.0 to find delta T. And finally, you also want to divide by the kilograms of the solvent. So 5.0036, that's the grams of the solvent naphthalene. We would divide that by 1,000 to get the kilograms. So delta T, 80.1 minus 75.0, 5.1 degrees Celsius. We'll use the grams as is. We'll use the KFP as is. We will convert the grams into kilograms of solvent. So 5.0036 grams would be 0.005036 kilograms. And you put all this together into the molar mass. There's the actual values. So again, there's G, there's KFP, this is delta T, and this is the kilograms of solvent. So when you put this into your calculator, and I encourage you to try, you get a number 131.7977. Now, because not only KFP was 2 sig figs, but delta T is 2 sig figs, you should round it up to 130 grams per mole. And this is the process you will use in this lab to find the molar mass of the benzoic acid. So in this lab, you're going to create a computer-generated graph of temperature versus time. You're going to have 3 sets of data, like we saw in the example, the Excel example I showed earlier. And you'll be able to see how the 3 sets of data, the solvent is the highest freezing point, and the solution with 1 gram is the next one, and the solution with 2 grams of solute will be the lowest of all. You want to find then the molality, and you can find the kilograms of the solvent based on the grams, and finally molar mass is going to be grams over moles. Now you can also use that equation that we used in the last example. It's totally up to you. People seem to prefer one way or the other. You do want to include a computer generated graph with your report. Make sure you get rid of any of that dead space. Don't have any dead space. You want to see your data up close, and make your graph a full page. All right, don't make it small. You want to have a big graph so you can see it easy and stuff when you're doing it. If you have any questions, of course, please let me know. The Learning Success Center / Avid Center can help with this kind of material as well. It should be pretty mellow. Okay, so at this point, we're going to watch a video and see how the freezing point lab actually works. It's kind of cool. This is a lab where you want to wear safety goggles all the time. All the chemicals in this lab are very fish unfriendly. They're very water insoluble, and they're not good for us either, to be honest. So man, make sure you got your goggles on all the time. Use protective clothing. Don't wear weird clothes and stuff just to make sure that you're safe. All right, if you have questions on any of this, let me know. Thanks for being here. Have a great day and enjoy the video.